Okay, yeah, I see the recording has started. Thanks, Zhang Yang, for organizing. So let me share my notes here. Great. All right, so yeah, the scope of this lecture series is to briefly but concisely introduce high energy physics to all of you, in particular collider high energy physics. And so during normal times, we would be in front of a blackboard and I would informally discuss some of these topics by drawing pictures and equations on a board, and I would happily be interrupted and answer questions from those of you who are in the audience. And in order to keep this informal, I've not prepared slides, so I have these lecture notes that I sent around ahead of time, which are the notes that I basically would be lecturing from a blackboard if we were in person. And so my vision is basically to go through these lecture notes. And please interrupt me if you have questions. I'll try to monitor the hands raised, and you can also just shout out if I don't see. And there's also the chat. You can ask questions. And also in the lecture notes, which I sent around to the email list, there are a variety of parts that are in red. So just you can see there are things in red, and the parts in red are sort of questions that you can try to make sure you understand what I said, and to follow up to see if there's some small calculation you can do to verify your understanding. I think that's all I want to say about the introduction. Today will be about the sort of the big picture, Large Hadron Collider in a nutshell, units and coordinates. So we're all on the same page. Many of you may be familiar with these topics, but I think it's important that we're all sort of using common language, and then there'll be more advanced topics in later lectures. All right, so maybe without further ado, I'll just dive right in. So first, yeah, is the big picture. So yeah, all of you are working in some way on topics related to the Large Hadron Collider. So the Large Hadron Collider collides protons. Protons are a type of hadron, and I'll say a bit more about what hadrons are later. And basically, hadrons are a class of composite particles that are made of quarks and gluons. And while protons are relatively big hadrons, they're not the biggest in terms of physical size. But the collider is what's large. So the Large Hadron Collider is physically very large. It's tens of miles in circumference. And we need that size in order to accelerate the protons to very high energy and collide them. And the protons are sort of depicted here schematically as sort of these three lines, and then some sort of potato-looking objects. And so the lines just represent quarks, and I'll say a bit more about that in a second. And we collide the protons nearly head on, and then hope to examine what happens from the collision debris. And so the first question is, why do we bother building this really high energy experiment? We've achieved the highest energy from any terrestrial experiment. And there's a footnote about terrestrial because there are experiments that probe higher energy collisions, but those collisions are basically astronomical in origin. And so there's no control over when they come, what they collide with. Whereas at the LHC, we have full control over the initial state. And so one reason to go to very high energy is because of this famous equation, which I'm sure most of you have seen before, which is that in order to create particles of a new mass, which are predicted by a variety of hypotheses for new theories of nature, we need to create a lot of energy. So basically, this equation says we can trade energy for mass. So if you want to make a mass of new particles, you better have a lot of energy. So that's one reason for high energy. And another reason for high energy is that more generally, in addition to looking for new massive particles, we want to really explore what nature looks like at the smallest distance scales. And so this is another equation that you're probably familiar with, although I suppose you're probably used to saying it without the squiggle and maybe a factor of 2. And the squiggle is just going to remind me that I don't have to think about factors of 2 here. But roughly speaking, this says that your uncertainty in position and your uncertainty in momentum the product is a constant. So that means that if you have a larger uncertainty on one, you can have a smaller uncertainty in the other, and vice versa. So if you rearrange this equation, basically, the h bar is a constant. So if I have very, very high energy particles, that's going to allow us to probe very small distance scales. And that allows us to sort of understand and examine the fabric of space-time in the smallest distance scales in a laboratory setting. And so in a way, you can think of the LHC as sort of like a microscope. And so here's the many decades of distance scales. And you can tell that we're studying particle physics here because I didn't bother putting anything bigger than a meter. Although, of course, there's a lot of interesting physics that goes in this direction. But if you imagine 10 to the minus 3 is sort of the smallest distance scale that at least I can see by eye. And then there's this whole range here that probes smaller and smaller distance scales. And smaller distance is sort of inversely proportional to energy. And so the Large Hadron Collider sits over here, and it's probing something like 10 to the minus 20, 10 to the minus 19, 10 to the minus 20 meters. And yeah, as I mentioned before, this comment in red, it would be good to understand where this number comes from. But roughly speaking, it comes from the fact that at the LHC, we collide protons with an energy of 6.5 tera electron volts. And I'll say a bit more about units in a little bit. And that gives us a center of mass energy of 13 tera electron volts, which can then be used to convert that into a distance scale, which is about 10 to the minus 20 meters. Okay, so that's roughly the setup, thinking about the LHC as a microscope. And I'll only say a bit more about what happens when we collide these protons. So as I mentioned before, protons themselves are composite particles. So even though we're colliding protons, the things which actually do the collisions are the objects inside the proton. So in particular, it's the quarks and gluons inside the protons that do the colliding. And the quarks and gluons inside the protons, they participate in the strong force. And the strong force is like electromagnetism that many of us are familiar with, except it has some interesting properties that make it quite different. So in particular, in electromagnetism, the photon mediates the force. That's the thing that's exchanged when particles participate in the electromagnetic force. In the strong force, the analog of the photon is called the gluon. And the gluon is pretty different than the photon in one very important way, which is that in electromagnetism, the photon is electrically neutral. And that means that photons don't interact with other photons. But in the strong force, gluons are charged under the strong force charge. So just like in electromagnetism, how you have the electrons have positive charge, and then anti-electrons have negative, or electrons have negative charge and anti-electrons have positive charge, and the photon is neutral. In the strong force, quarks and gluons have a non-zero charge, and gluons also have a non-zero charge. And so in particular, gluons can interact with other gluons, and so you get self interactions, which makes the force quite complicated. And as a result, the proton is basically a giant mess and is full of quarks and gluons. And so when we collide the protons together, it's sort of like colliding these bags full of particles. And then we get one quark or gluon from one of the protons and one quark or gluon from the other proton. They do the colliding, and then we get some interesting collision debris. And another interesting feature that results from this self interaction is that we don't get to observe quarks and gluons directly. And that's because when we produce a quark or a gluon, the strong force is so strong that the quarks and gluons, they radiate as they fly apart. And I have pictures here. So basically, you can imagine we have the protons, they're filled with quarks and gluons. The straight lines are quarks, the wiggly lines are gluons. And after the collision happens, so one quark or gluon here collides with some quark or gluon here, and then out goes some, they collide. In this case, two gluons collided, and there's out goes some collision debris. And the quarks or gluons, they fly away from the collision point, and they radiate. They radiate quarks and gluons, or they radiate gluons. The gluons, they can radiate other gluons. So here you have a picture of a gluon radiating a gluon, but the gluons can also split to quark-anti-quark pairs, and you get this shower of particles that is flying away from the collision point. And you get pictures that look like this, where the quarks and gluons, once they fly far away enough, they sort of cool down in a sense, and they form hadrons, sort of like the proton and the proton's cousins. Those are these light green pancakes, and then they can decay and form these little circles, which are other hadrons that we get to observe. Okay, so let me go back to where I was. Right, so we call that process of radiation, collimated radiation, a parton shower. And we associate the spray of particles inside sort of a small region of the phase space as a jet. So a jet is a collimated spray of particles that results from quarks or gluon produced at high energy. And there's not really a one-to-one correspondence between jets and quarks and gluons, but more or less, a lot of us think of jets as like a proxy for the initial quark or gluon that's produced. And I think we'll say a bit more about this in later lectures where we talk about the strong force. But now let me get to the fundamental particles. So the things that make up all the matter that we know about, there are quarks and they're quarks and leptons. So there are 6 quarks, and they have funny names: up, down, charm, strange, top, bottom. And they can bind together to form these hadrons. And bound states of 2 quarks are called mesons, and bound states of 3 quarks are called baryons. So the most familiar hadrons to all of us are protons and neutrons. So protons and neutrons are each formed of 3 quarks, so therefore they're baryons. So the proton is 2 up quarks and a down quark, and the neutron is 2 down quarks and an up quark. And together they are both baryons. However, the most common hadron at the LHC are not protons and neutrons, even though the protons are in the initial state. The most common hadron is actually the pion. And the pion is a composite particle made of only 2 quarks. So the proton is made of 3 quarks, so 2 up quarks and a down quark, whereas the pion is made of only 2 quarks, so it's easier to make. And it has less mass, so you can make more of them. And I made a little table, which I think now is down here. This little table shows you some names of some of the hadrons. So you can imagine if you have a meson is made of 2 quarks. So this is like one of the quarks and one of the other quarks, and together they form a meson. And so there are different kinds of pions. So they're charged and neutral pions. So the up quark has a charge of plus 2/3. The down quark has a charge of minus 1/3. And then the charm, strange, bottom, they also have these fractional electric charges. And so if you have like an up and an anti-up quark together, they're electrically neutral, and they form what's called the pi0, a neutral pion. And if you have a down, or say like an up quark and an anti-down, that gives you +1 charge, or an anti-up and a down that gives you -1 charge. That gives you the charged pions. And so you get a pi plus or minus. And you see that I've written pi0 twice. And that's because the pi0 is actually a superposition of up, anti-up, and down, anti-down. And I can say that more what that means later if you're interested. And then there are a variety of other more exotic. Is there a question?
I had a quick question. Is the top quark not included because it's the heaviest?
That's an excellent question. So indeed, the top quark is not included because it doesn't form bound states, because it has this interesting property. It's related to its mass, that it's so massive that actually it decays super quickly. And it decays too quickly to form a bound state. And so that's why it's not here. There are no top hadrons or mesons. Top mesons or baryons, because the top decays too quickly. But in principle, there would be another row and column for top quarks.
Okay, thanks.
Good question. Right, so there's the pions, and there are more exotic particles like the J psi, the eta, the upsilon, and various other particles you can see here. This, for instance, like the J psi, it's a bound state of a charm and an anti-charm. And it has actually, it's J/psi, that's the name of it. We call it the J psi. And it has, the reason it has 2 particles because it was discovered by 2 different groups and they couldn't agree on the name. And so there's why there's some funny history in some of these particles. This is just only a small list because you kind of have a sense of the mesons. And there's a sort of a corresponding table. You could imagine having like a periodic table also of the baryons, but it's more complicated because there are 3 quarks. And basically every combination that can be combined, to electrically an integer is possible. Okay.
Also, wait, really quick. These are those just the valence quarks? Like, aren't some of them composed of like more quarks than just 2?
That's a great question. So just like I said, the proton is really a bag of particles. So the proton, I think I said, is 2 up quarks and a down quark. But it's really filled with all sorts of quarks and gluons. So yeah, when I'm talking about, when I say that the proton is 2 up quarks and a down quark, really it means that the 2 up quarks and the down quark, they contain most of the momentum fraction of the particle. But there's all sorts of other things as well, and that can be formalized. but I can say a bit more about that later. But yeah, the jargon word is indeed valence quark. So these are like the main quarks inside the hadron, and then there's a bunch of other stuff that's sort of, you can think of it as sort of like orbiting around those main quarks. Yeah, that's a great question.
Okay, thanks.
Okay, so right, so I said about the mesons. Okay, so those are the quarks, and the quarks and gluons are the most prevalent particles at the LHC, but we're also interested in the leptons. And the leptons are also fundamental particles like quarks, but they do not participate in the strong force. And so in particular, that means also they basically don't form bound states. And so when we see a lepton, we just see it in isolation. It doesn't, we can just directly observe them more or less. And there are there are 6 leptons in total, 3 that are charged and 3 that are neutral. The 3 charged ones, so the lightest one is probably familiar to everyone. It's called the electron. The second lightest one is the muon, and the heaviest one is called the tau. And I've listed them in order of their masses. So the mass of the electron is really tiny. The mass of the muon is not so, still small, but not too small. And the tau is very heavy. The mass of the tau particle is basically twice the mass of the proton. And I'll say a bit more about the units in a little bit. The neutral leptons are called neutrinos. You've probably heard of neutrinos. And there are 3 different kinds of neutrinos, but more or less at the LHC, we can't distinguish them. So we just call them neutrinos. Okay. I think that's all I wanted to say about particles. Here's just maybe one big picture before I move on, where you have the protons, the pancakes with their incoming quarks, and they're filled with all sorts of particles, and they, in this case, radiate some gluons which collide, form some quark and gluon shower, and then those form the green circles, which are the hadrons that we get to observe in our detector, which you'll hear a bit more about in later lectures. So let me just pause for a second and see if anyone has any other questions about the fundamental particles or their interactions or how they form bound states. All right. So then I think I'll move on to units. And so units are, of course, super important for following any of the measurements that we make. And a variety of units are relevant. So one really important concept is related to the amount of data that we collect. And this may sound like a kind of silly thing to talk about, because you might say, well, if you just collect some number of collisions, like 10, 100, a million, a billion. But in fact, we collect so much data that we don't measure the amount of data we have in terms of number of collisions. That's sort of an astronomically large number. So instead, we measure things in terms of a quantity called integrated luminosity. So the luminosity basically is something like the rate of data collected. And we have this symbol. So L is usually the symbol for the luminosity, and the integrated luminosity has this symbol. So a little integral symbol, L dt. So integrating over time. So L is like the rate of collisions over time. And this quantity has some very silly units. So it has units of inverse barns. The barn is a very strange unit. So the barn is a unit of area. And so an inverse barn is a unit of inverse area. And it's a really tiny amount of area. So so an inverse barn is this number here, 10 to the 28 per meter squared. And one barn is really a small amount of data. So at the LHC, so far we've collected something like 150 inverse femtobarn of data, and you would pronounce it just like I said, 150 inverse femtobarns. And just as a reminder, so if you're not familiar with the femto prefix, this is 10 to the 15 barn. So pico is 10 to the 12, nano is 10 to the 9, and here we're talking about femto. Okay, so why do we measure data in units of inverse area? And that's because we measure the cross section, that is the rate at which something happens in units of area. So basically, and we usually use a symbol sigma. So sigma usually means a cross section. So if you take a cross section and multiply it by integrated luminosity, you get area times inverse area, and you get a number of events, which has no units. And in classical physics, the cross-section is related to the physical cross-section, so like literally the transverse size. So if you imagine like a proton has some physical size, and you could collide them, and then you might think that the cross-section is related to the physical size, which is what it would be in classical physics. But in quantum mechanics, relating the cross-section of various objects, can be calculated using a theory called quantum field theory. And I don't really want to go into the details of that here, but more or less the important point is that a barn, one inverse barn is a tiny amount of data, but one barn is a huge cross-section. And a typical cross-section for interesting processes that we care about is sort of like picobarn or less. Or keep in mind pico here, once again, is 10 to the minus 12 barn. So for instance, the Higgs boson cross-section at the LHC is something like 50 picobarn. And if you multiply 50 picobarn by 150 inverse femtobarn, which you should do later if you can't do it in your head, because I definitely cannot, this means you get millions of Higgs bosons that have been produced so far. Okay. Any questions about the barns and inverse barns before I move on?
Wait, okay, sorry. In the first paragraph, it says one barn is a tiny amount of data. And then like in the second paragraph, it says one barn is a huge cross section. Wait, is the first paragraph talking about an inverse barn or?
Indeed, that's a typo. I'll fix that. It should be inverse barn. Yeah. A barn is not an amount of data. Inverse barn is an amount of data. You're absolutely right. Yeah.
Okay, thank you.
Yeah, good point. All right. So the other. Oh, you have a question?
Yeah. So you said a one inverse barn is a tiny amount of data. So to make more data, you make it smaller because femto is okay.
Right. So we can so one inverse femtobarn is a lot of inverse barns.
Okay.
Yeah, and we make more data by colliding more collisions or colliding more protons, and that allows us to to get more data. So in particular, we can collide more. You can make L bigger or make or run for longer. Those are the ways you get more data. Yeah.
Got it.
Great. Okay. So the other kind of units that we care about are the physical units that we represent the systems that we're talking about. Now, in general, you can pick any units that you like, as you know, but some are more useful than others. And so you're probably familiar with like SI units, like the kilogram meter seconds. And that's really useful for expressing like the dimensions of our detector. Like the Atlas detector is like meters in size. And so that's like a useful notion. But when we talk about the particle collisions themselves, SI is not a very useful unit system. And so we're going to use instead what some people call natural units. And in natural units, instead of distance, mass, and time being the fundamental quantities instead are speed, angular momentum, and energy. And so we have sort of different units for each of those. So for speed, our rulers are going to be basically have length c, the speed of light. And for angular momentum, the rulers of angular momentum will be have length h bar, and for energy, the rulers will have length giga electron volts. And so in SI, if you have an object that has length 1, that would be like it has 1 meter long. It's 1 meter in length. So equivalently for us, an object that has speed 1 means that it's going at the speed of light. And so basically throughout your time in LHC collider physics, we are basically going to stop writing down the C's and H bars because they're just implied to be there to make things work out dimensionally. And so in particular, you'll hear us talk about masses, momenta, and energies all in units of GeV. And so you have to just, in your mind, remember that mass and energy have different units, but they're the same up to some powers of C. And in particular, you can always just remember E equals mc squared. So that means that energy and mass over c squared are the same. And so we're going to drop all the c's and c squareds from now on. And the same goes for h bars. So in particular, length and time are given in units of 1 over GeV, and their factors of h bar and h bar c are also implied. And with these rules, you can basically write any quantity that you like. You can derive the units for that quantity in terms of GeV. So we love GeV, that's our favorite unit. And in this table, you can see various quantities and then what units we use, basically. And so just walking through the table, so speed is dimensionless in this unit system because there's an implied factor of c. So if someone's going, if something has a speed of 1, that means it's going at the speed of light. And so if it has a speed of 0.3, that means that it's going at 30% the speed of light. Same for angular momentum. If something has an angular momentum of 1, it means it has h bar units of angular momentum and fractional, etc. And energies are given in GeV, and momentum and mass are also given in GeV, where actually there are some secret factors of c that we're just going to ignore from now on. And then same for time and length. They have units of 1 over GeV, and there's some h bars implied. And you can also, for fun, you can calculate what would be the equivalent units of other quantities as well, derived quantities. So for instance, like the electric charge is dimensionless, it turns out, and magnetic field has units of GeV squared, which you can work out if you put in all the factors of h bar and c to figure out exactly what it should be. And I think that probably the one number, if you only remember one number from this whole set of slides, the most useful number to remember is that the mass of the proton is about 1 GeV. So I never remember what the mass of the proton is in SI. Has some tiny mass. I guess I could read it off from the table. 10 to the minus 27 kilograms, I suppose. But for us, masses are measured in GeV, and so the mass of the proton is about 1 GeV per c squared. And we collide them at an energy of 6.5 tera electron volts, and tera is 1,000 giga, so 1,000 times. Basically, the protons are accelerated to an energy that's 1,000 times their mass, many thousand times their mass, actually. Okay, any questions about the physical system of units before I move on? All right, so then the last topic is going to be coordinates. So as is true for any math or physics class that you take, people pick a different coordinate system. So for us, we have a kind of a goofy coordinate system that's well suited for our purposes. So first of all, the most natural way of representing a particle's trajectory is in terms of 4 vectors. So hopefully you've seen 4 vectors before, but if you haven't, a 4 vector is not that different than a regular vector. And so, for instance, a spatial 4 vector, sometimes it's written x with the little mu superscript, and it has 4 components, as its name suggests. The first 3 are just the usual coordinates, so x, y, z, for instance, for a spatial coordinate. And then there's a 4th component, which for spatial coordinates would just be the time. And but we almost never use spatial coordinates. So the ones that we use the most are momentum coordinates. So you'll see a momentum 4 vector, and there the first 3 coordinates are the spatial momentum, so px, py, pz, and then the last coordinate is e. So p is going to stand for momentum, and e is going to stand for energy. And the Lorentz invariant quantity that p and e give is called the mass. So in particular, E equals mc squared is only true for a particle that has no mass or no momentum. It's not moving. That's its rest mass. And so if a particle is moving, the generalization of E equals mc squared is E squared minus p squared is m squared. And that's what's shown here. And this m squared here is just the invariant quantity, and it's the property of particles. Now, the other thing that's relevant is how we describe our detector. So we're colliding particles along a beam axis, and we basically pick the beam axis as the z direction. And then we have sort of a cylindrical symmetry about the z-axis. And so the z direction is the beam axis, and then x and y are perpendicular to that and perpendicular to each other. And so we have these sort of pseudo cylindrical coordinates that we use instead of Cartesian coordinates. And the coordinates are defined by these sort of 4 numbers. So you have to, it's sort of 4 numbers because you need 4 numbers to describe a 4 vector. So 1 is the transverse momentum, and we pronounce this PT. So you'll hear a lot the word PT. And this is usually given in units of GeV. And the PT of a particle is the magnitude of its momentum in the transverse plane. So it's px squared plus py squared in the square root. Then there's phi. So phi is the azimuthal angle, and usually it's given in radians. You'll almost never hear about it in terms of degrees. So that just to be clear, the azimuthal angle. So here's a picture of the sort of you can imagine the detector head on. So the z direction is into and out of the page. The protons are coming into and out of the page, and the collision debris goes in all directions. And so x and y are like this, and then phi, the azimuthal angle, looks like this. So it goes between 0 and 2 pi. And then we have this second coordinate, which is a bit goofy, called eta. And eta here is the pseudo rapidity. And it's this kind of crazy transformation of theta. Theta is the polar angle. And so if this is the transverse plane, this is the head-on plane, or this is the looking at the collisions from the side. So in this picture, the protons come in from the left and from the right, and y faces the sky. And you can see theta here, the polar angle, tells you the angle between z and the transverse plane. And instead of using this quantity theta, we use this quantity eta. And you can see that there's a one-to-one correspondence between theta and eta. But we almost never use theta. We almost always use eta. And I'll say a bit more in a second why that's the case. And then for a fourth number, we often use the mass because it's invariant. So it's quite nice that way. And it's given also in units of GeV. Now, eta here, it's not an angle, but we often think of it as an angle. So we're often talk about the magnitude in terms of PT, and then the angular coordinates eta and phi. Okay. So now I'm going to spend.
Sorry. So
yes.
Really quick. So these
Please.
coordinates are combining kind of like the momentum coordinates and like the Cartesian like x, y, z, t coordinates, kind of.
Right. Good question. So so basically, we want to express a 4 vector like this, and we're just reparametrizing that. So if I give you PT, eta, phi, and m, you should be able to derive px, py, pz, and e. And so in particular, px is pt times the cosine of phi. Py is pt times the sine of phi. And it's a little more complicated, but pz can be expressed in terms of the hyperbolic sign. So I think it's pt sinh of eta gives you pz. And then e is, once you have px, py, pz, e is just px squared plus py squared plus pz squared plus m squared square root.
Okay, and then yeah. Is there also Lorentz invariant for these coordinates?
So the m is the Lorentz invariant. So basically, instead of giving it in terms of px, py, pz, and e, we usually give it in terms of these coordinates and their invariant. And from this, you can back out the energy if you wanted to. We sometimes do,
okay.
But we usually just give the mass. Yeah, but these 3 are the ones that give you like the spatial momentum. So like I said, PT, and then you can compute px, py, pz if you like, and then we give m the invariant, and then you can compute energy if you wanted to. Yeah.
Okay, thank you.
Great. Yeah, any other questions? Okay, great. So now I basically want to spend the rest of the time talking about pseudo rapidity. It's kind of a goofy quantity. So yeah, why do we use pseudo rapidity and not just the polar angle? And the answer is that it's kind of complicated, but let me just try to give you the brief version of it. So we collide protons with the same energy. So the center center of mass frame of the proton-proton collision is the lab frame. That is to say that in the center in the lab frame, the proton-proton collision is not moving. However, I also told you that the protons are not the things that actually do the colliding. So inside the protons, there are a bunch of particles, and those are the particles that do the colliding. And even though the protons have equal and opposite momentum, the particles inside the proton do not. So each particle inside the proton carries some different momentum fraction of part of the proton itself. And so imagine you have a quark from one proton colliding with a quark from another proton. Those two quarks need not have the same momentum fraction of their parent proton. And so the collision, the individual, we call it parton-parton center of mass frame is not the lab frame. It's moving along the z direction with respect to the lab frame. Now, it is definitely the case that all the collision, even the parton-parton frame in X and Y is the lab frame, because all the constituents inside the proton are basically confined to moving along the z direction. So X and Y are good coordinates. They are the same for us and for the collision, but the z direction is a little bit special because the center of mass, the actual parton-parton collision is moving with respect to us along the z direction. And so we'd like a coordinate that has a nice transformation property under transformations along z. So in particular, boosts along the z direction in terms of Lorentz transformations. And so PT and phi, if I boost along z, they don't change because coordinates that are perpendicular to the boost direction, they don't change under Lorentz transformations. And so PT and phi, untouched. And so all that so if I go back to the coordinates, if I boost along z, PT doesn't change, phi doesn't change, and m doesn't change. M actually doesn't change if you do any Lorentz transformation. These only don't change if you do a transformation along the z direction. However, this coordinate does change if you boost along the z direction. And the reason we choose this coordinate is because it has a really nice property. And in particular, the property is shown right here, which is that if you boost along the z direction with some velocity, so imagine you have a velocity beta, and you boost along the z direction, your new coordinate transformed linearly. So if you've taken special relativity before, you'll probably remember that the velocity transformation formula is really complicated, right? If you have some velocity and then you move with respect to that with some other velocity, the new velocity is some complicated nonlinear combination of the two velocities. But for pseudorapidity, it's extremely simple. If I have some pseudorapidity and I'm moving at some velocity beta with respect to the initial frame, the new pseudorapidity is literally just the old pseudorapidity plus a linear a linear offset that depends on beta. So in this case, it's the hyperbolic tangent inverse of beta, the velocity. And so this is super nice. And in fact, because I never remember the velocity addition formula, I always start with this, and you can derive the velocity addition formula from this if you like. But one of the reasons this is so nice is because imagine now I have two particles that have different etas in one frame, and now I boost along z into a different frame. Each of those etas gets the same linear transformation. So the two etas get transformed like this. So that means that the difference between the etas does not change. And so in particular, the difference between the etas of two particles is invariant under boost along z. And this is basically the main reason why we use the pseudorapidity, because we don't know the initial boost of the center of mass of the two partons that collided. So we don't actually know what beta is, but I take the difference in eta between two particles, it's the same no matter what rest frame you're in. And so with respect to boost along z. And so that's a good quantity independent of that boost itself. I'll pause there for a second to see if that argument made sense.
Wait, sorry, can you explain what you mean by a boost in z?
Right.
Specifically.
So, yeah, so let's say I'm in the lab frame, and in the lab frame, the lab frame is the same as the proton-proton rest frame. But now imagine that I have an observer who is moving with a velocity beta along the z direction. right? So that's a different frame. And by boost, I simply mean, let me go from my frame to that frame. So in the frame that's moving with velocity beta along the z direction with respect to my frame, me being sitting there in the, with the detector not moving, I want to know what the eta is in the moving frame. Does that make sense? So boost just means go to a different frame.
Okay, yeah. So then you're saying that like the change in the eta in your frame would be the same as the change in the eta in the boosted frame?
Right, yeah. So if I have two particles that have different etas in my frame, the etas themselves will change if I go to a different frame, but the difference in etas is the same.
Okay, that makes sense.
So
and
like
then
in a sense, oh, go ahead, sorry.
All of the other quantities would just stay the same.
Exactly. So in particular, if I boost, that is, I go to a new frame along the z direction, pt and phi and m don't change, and eta does change in this linear way. But if I have, but distances between particles and eta don't change. Yeah. And that's why this is sort of a really nice quantity.
Okay, that makes a lot of sense. Thanks.
Cool. Okay, so I think, right, that's all I want to say basically about that. And then a couple of other related quantities. So you might hear us talk about delta R. And so we're going to often think about eta and phi kind of on equal footing. So even though eta and phi, even though eta is not a true angle, we often talk about distances between particles in sort of delta phi and delta eta. So delta R is basically the distance, the Euclidean distance in phi and eta between two objects. So I have two particles, I can compute how close they are in delta R. And I just told you that one really nice property about delta R is that it's invariant under boosts along the z direction, right? Because delta phi is invariant because it doesn't change if I boost along z, and delta eta is invariant, like I just told you. And so in particular, when we talk about like how close electrons are to jets or how big a jet is, we're always going to talk about delta R. This is sort of like our usual measuring stick for how big how big objects are in a Lorentz invariant kind of way. Okay, so then I'm going to end with just one last note about pseudorapidity, which is that all the properties I've just told you about pseudorapidity, like this nice transformation property, the linear one, it only applies if the particles are massless. So if I have a particle which is massless, that's how its coordinate transforms under Lorentz transformation. For a massive particle, eta does not transform linearly. Now, for most of the particles we care about at the LHC, their mass is basically negligible. And so in particular, imagine I have a proton, which has a momentum of like, I don't know, a few hundred GeV. Its mass is 1 GeV. So the mass over the momentum is tiny. And so it's more or less a good approximation that protons for most purposes at the LHC are massless. Same for electrons and muons and most of the other particles. We can basically approximate them as massless, and we can happily use eta to, as a really good approximation of their coordinate. But some particles are massive, and it turns out there's a generalization of pseudorapidity for massive particles, which does have the linear transformation property, and that's called rapidity. So you may have wondered, why is it called pseudorapidity? And that's why. So the more general property is called rapidity. So rapidity is sort of like the particle physicist version of velocity. We like using rapidity because it has a linear transformation, whereas the velocity has this kind of crazy nonlinear transformation. And the rapidity, which has it's called y, and I apologize, but that's just what we call it. It's not the same as the y dimension, confusingly. It has this notation here. So let me contrast this with the pseudorapidity. So pseudorapidity depends on this angle theta in this way, the log of the tangent of theta over 2, whereas the rapidity depends on the energies and momenta in this way. And at first glance, those two formulae have nothing to do with each other. They seem totally different. But a useful exercise for you to do is to show that if the mass is really small, then rapidity and pseudorapidity are the same. And so in particular, you can show that if the mass is tiny, that means that the energy is well approximated as the magnitude of the momentum. And you can, I think I gave you some hints. There's some hints down here. So if you use some of these hints, you can plug those into this formula, and you can show that this formula, in the case where E and P are the same, this just reduces to the geometric definition of pseudorapidity that I showed you earlier. And I think that's basically it. So I covered today just finished coordinates. We talked about units. We use natural units where C and H bar are 1. Everything is given in units of GeV or inverse GeV. And then in terms of the big picture, the goal of everyone's goal basically is to try to probe the smallest distance scales that are possible, be it looking for new particles or other new forces of nature, structures that are at the subnuclear length scales that we can probe basically for the first time with these very high energy collisions, the Large Hadron Collider. So let me now stop there. And if anyone has any other questions about the big picture units or coordinates, I'm very happy to answer them.